Dimension simply connects or shows relationship between a derived quantity and a fundamental quantity. If you watched the video in my previous classes, you see that I mentioned this. This is what we call a physical quantity. When I talk about physical quantity, I talk about fundamental, derived, and also supplementary. But supplementary is just by the way. Okay, the two major ones we have are the fundamental and the derived quantity. So dimension simply talks about the nature of a physical quantity and shows the relationship between derived quantities and fundamental quantities. In other definitions, we can say that a dimension or dimension of a physical quantity is just the power at which a fundamental quantity is raised to express a physical quantity. Usually, you find something like when you start solving and you understand that, find something like m raised by 1, l raised by 2, t raised by minus 2. Now, these letters here are the dimensions of fundamental quantities. You can see that they are all raised to a particular number. They are raised to a particular number. That's why I said the dimension of a physical quantity is defined as the power to which the fundamental quantity, which is this MLT you are seeing over here, is raised. Okay. And I also said that it shows relationship between a derived quantity and a fundamental quantity. Now, talking about fundamental quantities, I mentioned in my previous video that we have about seven fundamental quantities. Seven fundamental quantities. Let's see if we still remember. We have length, we have mass, we have time, we have current, we have luminous intensity, we have amount of substance, and we have temperature. These are the basic or the base quantities that we have, or fundamental quantities that we have. So each of these fundamental quantities, they have a dimension. Okay. But basically, we deal with just three. Basically, for now, we deal with just three. Okay. Dimension for length is L. Dimension for mass is capital letter M. Dimension for time is T. Don't get me wrong. Other ones also have the dimensions. Like for temperature, usually they use K, sometimes they use theta. Okay, for current, they use A for the dimension of current. Okay, but for the purpose of this video, we're only going to look at the dimension of length, mass, and time and see how we can use it to relate to other derived quantities. So let's take a look at some derived quantities. First, we have area. Area is defined as length times breadth. Okay, so what will be the dimension of area? First, don't forget that the dimension of length is L. Okay, we just did that up there. And dimension for breadth is also talking about distance, talking about length. So dimension is also what? L. So what will be the dimension here for area? Dimension of area will be, for length we have L, and for breadth we also have L. So what will be the dimension? This is going to give me L square. As simple as this. You can see this L square now is telling us the relationship between the physical quantity and the fundamental quantity length and the derived quantity area. Let's take a look at velocity. Velocity, we know it's, by definition, velocity is displacement over time. It's displacement over time. Okay. So what will be the dimension for velocity? What will be the dimension for velocity? Let's take a look at it. Here we have the dimension for displacement. Displacement talks about distance in a particular direction, which also talks about length if you think about it. Okay. So that means that displacement is going to have the same dimension as length, which is what? Which is L. All right. And time also has a dimension. I gave you three dimensions up there. I gave you dimension for mass, for length, and for time. For time is capital letter what? Capital letter T. So that means the dimension for velocity is L per T. Usually you write this in indices, in form of indices. Okay. Let me just break it down. This is L times this T. I can write it as 1 over T. Don't forget, this can give me L times 1 over T is same as saying T raised by minus 1. So the dimension for velocity now will be what? LT raised by minus 1. Looking at acceleration, acceleration is defined as velocity over time. Velocity over time. Okay. Now, what is the dimension for velocity? We just got that up here. We got that as what? As L. Sorry, let me change the color. As LT raised by minus 1. Okay. This is over the dimension for time is T. This is obviously saying T raised by 1. So applying the principles of indices, this is L T raised by, we have minus 1 up here. Division in indices, division will become what? Subtraction, minus. Then we have what? 1. Now I picked one of the base because they are the same. Okay, if you remember the principles of indices. So what's it going to give me? It's going to give me LT raised by minus 2. So this over here is the dimension for acceleration. Let's take a look at force. Force is simply mass times acceleration. There are different ways of getting the dimension. Okay, I prefer solving it this way. Acceleration. I think this is the easiest way. I think this is the easiest way. Okay. All right. Mass is simply what? The dimension for mass is m, isn't it? Is m. And dimension for, now mass is m, is a base quantity. The dimension for acceleration, we got that up here to be LT raised by minus 2. So what's it going to give me? This is going to give me MLT raised by minus 2. Very, very simple. It's very easy to get dimensions. Very, very easy. Let's look at pressure. Pressure is simply force over area. Force over area. Okay. What is the dimension for force? We got that up here to be what? To be MLT raised by minus 2, isn't it? Over area. Dimension for area, we got that up here. Let's come back up here. We got what? L square. So this is going to give me L raised by 2. So everything here will give me M. You can see we have L here, we have L here. So you apply the laws of indices. This is L raised by, the L here has raised by 1. So this is L raised by 1. This is divided by L raised by 2. Division becomes what? Subtraction. Okay, sorry for that. L raised by 2. So that will give me minus 2. Then T raised by minus 2. Our final answer here will be M L 1 minus 2 should give me minus 1, then T raised by minus 2. So this over here is the dimension for pressure. I think that's clear. For work, we know that work is simply force times distance. Okay. The dimension for force, we got that up here to be M L T raised by minus 2 times dimension for distance is L, because distance is also talking about length. Okay, so what's it going to give me? It's going to give me M. Since we have L raised by 1 and L raised by 1, we have L raised by 1 plus 1. Why am I adding in this case? Because we're having multiplication. When you have division, you subtract. Okay, then T raised by minus 2. So what am I going to have? I'm going to have M L raised by 2 T raised by minus 2. Let's take a look at some other example. Let's take a look at energy. Energy can be potential energy, can be kinetic energy. Let's look at potential energy. We know that PE, potential energy, is equals to mgh. mgh, which means mass times acceleration due to gravity times what? Height. So what is the dimension for mass? Mass is m. The measure for acceleration is LT raised by minus 2. You can recall that up here. Okay. And height is talking about distance, which is also length. So what's it going to give me? It's going to give me M L raised by 2, because we have L raised by 1, L raised by 1. That's 1 plus 1, 2. Then T raised by minus 2. And what do you notice? You can see that both work and power and energy have the same dimension. The same dimension of ml square t raised power minus. This is why I mentioned earlier that dimension shows relationship, okay, between physical quantities. Now, this now is showing us relationship between work and what and energy. Take a look at the dimension of a different quantity called density. Again, density is mass over volume. So what will be the dimension? Don't forget the dimension for mass is capital letter M. And volume means, let's bring this down, let's bring it out. This is length times breadth times height. So dimension for length is L, dimension for breadth is L, dimension for height is also L. So this is going to give me L times L times L. That will give me L raised power 3. So bring that here. What are you going to have? This is going to give me L raised power 3. So our dimension here is ml raised by minus 3. In case you don't know how I got minus 3, let me break that down. This here is going to give me m times 1 over l raised by 3. There's a law that says that this here, that's this, will be equals to, sorry, this is times, will be equals to l raised by minus 3. It's a law of indices, okay? So when you multiply this, what do you have? ml raised by minus 3. Take for example, the third dimension of pressure is m raised by x, l raised by y, and t raised by z. We're now asked to find the value of x, y, and z. We're told that this here is a dimension for pressure. Now, when we sub it up here, let me go back. Where is it? Pressure. We got the dimension of pressure to be ml raised by minus 1, ml raised by minus 1, t raised by 2. Now comparing this to this, comparing their powers, you can see that x is equals to the power of m, which is 1, y is equal to the power of l, which is minus 1, and z is equal to the power of t, which is what? Which is 2. This area of dimension is called dimensional analysis. In the next video, we're going to be solving tougher questions on dimensional analysis.